which means taking storage off-chain. Right now, this seems infeasible because of the cost of call data. So let's take an example, layer 2 contract. So the cost of call data is 68 gas per byte, which means 2,176 gas per word of 32 bytes. Now let's take a sidechain that can accommodate 2 million users, each with a balance in 2 different token types. These are the rough numbers that we consider a minimum viable product at 0x. This won't even take us like to the whole world is tokenized scenario, in which case we would need 1 million tokens and 1 billion users. Anyway, this will already bring you to a balance tree that has 32 layers in it. So a Merkle proof in this balance tree is 32 words, which means 70,000 gas of call data. Verifying it is super cheap. Like it's a couple of SHA-3 operations, you do a couple of call data loads. It's only 2K gas to verify this proof. But compare this to doing a storage update of a same single balance. That's only 5K gas. So we're talking about a more than 10-fold more expensive solution to bring it off-chain. This makes this entirely unfeasible right now. This makes us, right now, use storage for balances instead of taking this off-chain. This problem actually gets worse once you look at more sophisticated solutions. Starks right now are limited by call data. You can verify a Stark in EVM fairly easily. You don't even need a precompile for that. The problem is that Starks contain a lot of Merkle proofs, and these Merkle proofs right now cost millions in gas. It's hard to stay under the gas limit purely with the call data. So if you want Stark-based layer 2 solutions, call data needs to become significantly cheaper. Another thing is fraud proofs. I know that the TrueBit people, they have this mechanism where you can submit a fraud proof of incorrect execution. And they had trouble keeping this fraud proof, which contains a lot of Merkle roots, to the memory that was used in WebAssembly. They had trouble guaranteeing that this fraud proof would actually stay under the gas limit. And if you have a system that depends on fraud proofs, and you can't guarantee that the proof actually fits in a block, your system is up for disaster. Like, someone can do something fraudulent and you would not be able to prove this on the mainnet. So it's essentially useless that way. Another thing is, take for example the mini-me token. This is a token that uses a tremendous amount of storage because it keeps all the old balances around. And the main purpose of doing this is that you can do things like forking a token at old balances or implementing voting mechanisms that uses balances at a certain point. There's a much more efficient solution for this, where you just use a Merkle proof of balance to an old block hash, or to a particular block hash or state root snapshot that you store in the contract. But right now this is also infeasible simply because of the cost of Merkle proofs. So where does this number come from, the 2,176 gas per word? And Vitalik, please interrupt me if I get this wrong. But the way I understand it is that it started out with a particular maximum call data block size of around 120 kilobyte. Then divide this by the gas limit. And this will give you the minimum amount of gas required to ensure that the call data is always under a particular threshold. So basically, it's starting from what is the most adversarial scenario of call data, given the gas limit and the gas price of it, and how do we need to set the gas price to prevent this from happening. I'm not exactly sure where this 120 kilobytes itself comes from. This could be either like chain growth-esque stuff, where we don't want the chain to grow with more than a maximum of 1 gigabyte per day or something like that. It could be a bandwidth issue where transaction propagation grinds to a halt if we go over this limit, or it could be a block propagation issue where blocks themselves don't move fast enough as soon as we increase it. I'm hoping that Zach can come up with a decent answer here soon of what actually breaks if we up this limit. That being said, in practice, we don't even get close to this call data block size. According to Etherscan, the average block size is about 20 kilobytes. I assume that this contains more than just the call data and also maybe transaction receipts, but I don't know how Etherscan IO computes defines block size. At any rate, it's 20 kilobytes and it peaks under 40 kilobytes, so we're nowhere near the limit. So I also want to quickly reflect on what other uses does call data currently have. So the main use of call data is to argue for state chains. It is basically proof like some signatures, some meta information that the state should move from this state to the next state. There's some auxiliary use cases that people have sporadically used, such as proof of knowledge. You can submit a hash of a document to the blockchain. It gets stored in the call data, and then I can always claim in court that I had this document in my possession before a certain time. Same as proof of publication. Some algorithms require data availability things where you need to prove that you actually publish certain things. You can store that in call data. And the other is just simply use the Ethereum blockchain as your own like distributed file system. I would argue that only the first is an appropriate use of call data and the rest should revert to logs and storage instead. So I would argue that we can ignore all the other use cases, make it only for state transitions, and therefore make it security-wise safe to prune as soon as a decent amount of consensus and finality exists on a state. So given all that, I propose the following. First of all, remove the zero non-zero distinction. Didn't really get into this during this slide, but basically this is a remnant of using a run length encoding in the wire format, which to me seems like an overemphasis in the gas model on a particular implementation. And as far as I understand, this run length encoding isn't even used anymore. And right now people are mining Ethereum addresses that have the maximum number of zeros in them, scattered throughout the address, which doesn't even help for run length encoding. So yeah, I think this can go. I would also argue that we should lower it to 100 gas per word in order to make Merkle proofs economically competitive with chain storage. Now, this has the immediate consequence that the maximum call data size of a block can increase. So I would say we can add an additional limit for a valid block. So a block is only valid if the combined call data size is less than X, where I suggest as a starting point we make X twice what the current maximum is, 256 kilobyte. And then in order to make sure that chain growth and things are kept in check, we aggressively prune call data under the assumption that it's only an argument for state chains that then doesn't have any further usage. And that's my presentation already.
So I can give some more context about the zero non-zero thing. Basically, the issue is that before we introduced that, what happened is that people started feeling the need to kind of really optimize the hell out of their Solidity functions, and instead of packing variables into 32-byte values, they would spend a lot of time deciding whether it's an int2, an int4, an int8, or like an int whatever. And the goal of this is to basically just make writing contracts much simpler, and so you can make everything be a 32-byte field, which is really much more convenient for contract programming and not have to worry about it.
Thank you, that's a good point. That's also part of the reason why my proposal moves to a gas price per word instead of per byte.
Right,
so
but the problem is that you could even still kind of get efficiencies by packing multiple arguments into 4-byte things in one word.
Gotcha. Do you think that's still feasible if the gas price is 100 gas per word? Because then the overhead of packing becomes more significant.
Right. Yeah, I mean, it'll definitely become like better, but 100 gas per word is basically 3 gas per byte, which is 20x decrease is significant. And I'm also kind of scared of this kind of hybrid rate and limit issue because it changes the miner's optimization problem to this weird multi-dimensional thing that requires more complex math to figure out. But I guess like the core of the proposal is probably just reducing the limit and aggressively pruning call data, which seems like fine.
So if you've got 256 kilobytes per block, that's about like half a terabyte of blocks a year. So I think that it's
6 per block multiplied by multiplied by 6,000 a day, which would get you to 1.5 megabytes a day, and then multiplied by 300 days in a year gives you to half a gig a year.
yeah,
Yeah.
no,
Yeah, so
half
it's
a
not-
terabyte because it's a gigabyte per day.
Oh, hold on, no, it's 56. No, it's yes, you're right. Okay.
Half a terabyte per year.
Yeah, that's yeah. So it would require running.
Is that what your comment was?
Yeah, I don't like running.
I wanted to ask, if you go back to your previous slide, when you were describing the uses for cold data. So interestingly here, where you said that the other usages, like for example, distributed storage number 4, is that we were actually going on about the not using storage for like, for as a contract storage is basically like a really valuable resource. It's probably more valuable than the cold data because it could be accessed from the smart contracts. So I would rather say if you want to distribute storage, you should really use cold data instead of the storage.
I-
The point here is that if you want to use the blockchain as a very high availability data store, then the kind of the officially sanctioned way to do it would be to have it in cold data and put the cold data into a log. And you can
Exactly.
use a gas for a log, but there would be more time guarantees that the log actually assembled more time, or the transaction data would be faster to use forever.
Exactly.
So I would say this is actually very interesting in the context of chain pruning. So and in the state rent as well. So it sort of encompasses all of these things. So what are the, I think what we could get out of this is a recommendation for like how the storage should be used and what in which cases cold data should be used instead, or in which cases a log should be used. Anybody else have any comments?
So yeah, the main takeaway from this is that as much as we would love to use a state root in storage and basically run 0x at a fixed storage size of only a couple of bytes, right now it's simply infeasible because of the cost of Merkle proofs.
Yeah, I'm a little confused about this slide too, because in order for something in order to, you know, emit a log or go into storage, it has to come in through the call data in the first place.
Right now, there's people who just send transactions that shove stuff into call data just for the point of having the data be there, right? So, just like one random use case for this to give people context is, let's say I want to have a DApp that is just accessible from one line of Web3 code, which would basically say load up the get raw transaction of this, then dehexify it, and then execute that as JavaScript. And like that would let you have dApps without having to have centralized UI or whatever. Like it's obviously a stupid workaround, but there's reasons to do it. So if you want to do things like that post this change, then you would have to have the transaction, but then you would also have to log the data. And if you don't log the data, then the transaction data just becomes like not accessible easily after a couple of weeks.
That might happen anyway with logs and.
Well, the point is that the guarantees for like the basic, think of it as kind of like a hierarchy where transactions are very ephemeral, logs are kind of medium ephemeral, and storage is forever but costs forever.
I think we can also have a discussion to which extent we want Ethereum to be used for bulk storage as opposed to solutions like Filecoin.
I think there's a hierarchy here because like there's a difference between storing a few hundred bytes and storing a gigabyte of cat picture files. So I could actually just give one motivating use case of extremely high value use of the blockchain to store even like 50 bytes. So let's say you want to have some a brain wallet or something hidden behind basically a file encrypted with some password or something like that. And instead of one password that you might forget, you might want to have it say be a 3 of 5 of passwords or other things that you remember. Now you can make a 3 of 5 with secret sharing, but the problem with that is that with secret sharing you can only choose your first 3 pieces of data, and your other 2 are basically randomly generated stuff based on the first 3. So what you do instead is you choose all 5 pieces of data, then you use erasure coding to extend that to 5 out of 7, and then the 6th and the 7th are random junk, but you publish those to the blockchain, and now you can recover data with like any 3 of 5 human memorable things plus 2 random things that are publicly viewable. So there's a bunch of like really cool tiny things like that where like the value of storing data is extremely high per single byte, and so using the blockchain arguably is really optimal for it. But it's definitely not the same as like videos.
I would also say one more comment. Although it might have been designed that logs should be sort of cheaper to store than the cold data, but in practice, the growth of the log is already faster than the growth of the cold data. So it's already like if you look at the archive node that I'm running, the size of all the receipts is already larger than the size of all the blocks, which answering your question, it pretty much contains the cold data plus some addresses. So yeah, I think it's like whatever the intention was, the current log usage tells us that it's already like. So I would start pruning the logs more aggressively than the blocks already because they are actually growing faster.
So then, my guess is that actually use cases 2, 3, and 4 are really sporadic.
Yes.
But right now the logs don't really differentiate between the sporadic uses versus signaling that some token did some transfer.
And also one of the big differences between sort of narrative of the Ethereum kind of syncing and Bitcoin is in Bitcoin essentially there's only one way to sync the chain is to do the from Genesis, and because they don't have the state roots in the blocks. So essentially the blockchain is one giant Merkle tree. In Ethereum, however, you have ability to sync from the snapshot, which means that it allows you to prune everything and still sort of have some kind of version of so basically, theoretically, even if the whole network removes the first few blocks, and it becomes unavailable, we can kind of still go on, right? We can still go on producing new thing. We just don't know what was in the beginning. And I think that tells me that the storage the space in the state is more precious than the state in the blocks. So and it has to be. And what you're saying is that it's actually looking at the gas cost. It's the other way around. So it's actually easier to put stuff in the state rather than to put it in a cold data, which should be reversed.
Yeah, that's the main point. When it comes to your point on log messages, so if we were to do security critical information in log messages, they would get mixed in with a lot of not security critical information that we would love to prune. So then the argument would be to not use log messages for points 2 and 3, but instead use storage directly, because we do have security guarantees that storage will be maintained forward. And then we can aggressively prune both call data and log messages.
Yeah. Secondly, I wanted to thank you for running these numbers. This is super relevant. But about a block size, so I'd hesitate to introduce a block size limit unless we want to have not just a guess limit debate, but also a block size debate.
Isn't it going to be fun?
I mean, right now we're nowhere near the current limit, but the assumption is that if we move to bulk off-chain storage, we will get a significant increase in Merkle proofs that are submitted to the chain. So you can expect a significant uptick in the block size. And then
Right, but
if you then do this 10 times gas increase, you also have a 10 times block size increase. So it already becomes 1.2 megabytes, which is something worth discussing in its own right.
Not sure it would be like that bad in practice to not have the limit, because without it, like the block size without the limit goes up to 68,000 words, which is a bit more than 2 MB, and from there, like, I mean, first of all, that's only a factor of 8 more than this limit, and I think you can totally make reductions that are more modest than to 100 gas a word, and like second, this is one like big blocks are one of those areas where if they're too big, your uncle rate goes super high. So there's also a natural disincentive to not make very big ones. But
Yeah, we'll have to discover what the uncle rate, like what the
yeah, you
Yeah.
know,
The effect is
definitely
on the uncle rate.
I'm looking forward to like seeing regressions on like what the uncle rate contribution for block size is as opposed to other things.
and those can be ameliorated with optimizations on block propagation.
Just a minor comment that we've observed that uncles are smaller than regular blocks. So block size is not the impact that we think it is. That's it.
So that basically justifies that some reduction from the status quo is like good, but the question is how big of a reduction? Because you still want to kind of keep it balanced relative to other stuff. And it seems like if our goal is to make Merkle proofs be the cheaper way to build these kinds of applications, then like we're actually attacking that problem from two angles. One of them is making the call data cheaper, and the other one is making storage slots more expensive.
I mean, that is the goal. It's the only option.
Yeah, you know, doing both is.
But then there would be more pressure on improving on the change.
Yeah, just to clarify, this limit on the block size, if we can do without, that would be better for me, of course. Thank you.
Okay, so I'm here here to talk about uncle rates. So the previous conversation kind of flows nicely into this. We've been looking at the data historically of uncle rates. And then just to give some context, uncle rates are still blocks that get mined and included into the chain. They get some reward, which is about 7/8, depending on when it gets referenced in the main chain. And you also get a reward for including an uncle. And so why is this important? It can help you see what the state of the network is. Higher uncle rates are theoretically related to lower block times and also to a larger size. But it's not necessarily the case, as we've noticed in the last 6 months. So we look at the uncle rates historically, and then we find different points in time where you have interesting changes. So you had some hikes in August 2016, which is the DAO, or like another fork in November 2016, and so on and so forward. But for us, what's been most interesting is this drop in the last 6 months of the uncle rates. It just seems to have been going down, which is interesting because the number of transactions per block doesn't seem to be going down. So there's not necessarily a relation between the transactions, the size of the block, and the uncle rates. And so the idea of this is to make it a little bit more interactive for you to give us also some ideas of why this might be happening and some of the implications of this. So essentially, this is just like a closer look in terms of the last 6 months. And as you can see, the transactions doesn't really match this slope that we see in the decrease of uncle rates. And so we just thought about a number of different possible causes for why this could be happening. So maybe the data size is more important than the transaction count. Maybe it's the number of miners or the number of nodes, protocol changes or the parity and get optimizations, or changes in the miner strategies. Maybe an increased connectivity between the miners, or since there's a migration of a lot of nodes and miners into Amazon, maybe that's also causing better connectivity and thus resulting in lower uncle rates. And so we started testing all of these hypotheses. We have collected data from Alethio, Etherscan, and Etherchain, and we're going to share all this data so that people can also start doing their own analysis. And essentially, these are the variables that we've used, so they're all numbered there. And so we started checking the number of miners, which doesn't seem to have changed much in the last couple of months. So if anything, there's a little bit more miners, so it doesn't seem to be related to the uncle rates. We can also see that there's a lot of centralization. So if we look at the top 20 miners, historically, it has decreased a lot. Now you have like only 5 main pools that have most of the hashing power. So that could explain also the increase in connectivity and the drop in uncle rates. But it's not conclusive. And these are the mining pools that have been doing the most mining of uncles in the last 6 months. So we started theorizing what could cause this, maybe some collusion or selfish mining, but it seems very unlikely in terms of the results that we found. We did find this curious increase in number of empty blocks in the network. There's been an increase of about 3%. There were some articles that came out about a couple of months ago in October that were claiming there was spy mining happening in the network, but we talked about this morning with Vitalik, and it seems that that wouldn't be possible. But it does seem that there's an increase in terms of empty blocks that have been getting mined in the network. So again, we tested this idea that miners would stop working on blocks as they receive the header from other miners, and since they don't have complete information, all they can do is post empty blocks. But it doesn't seem to be the case. We were also looking at these empty blocks and finding that the data is a bit inconclusive, as you might have higher block size than the uncle size or the inverse. So we're a bit puzzled by why this is happening. And so like you can see here, you can see the size of the uncles on the first column and then the size of the blocks on the second column, and you just see variation. Sometimes the uncles are bigger, sometimes the blocks are bigger. And so we started doing some analysis in terms of this data and trying to see what could be causing this behavior. So yeah, we also checked the number of nodes, but it doesn't seem, it might have an effect in terms of less participants in the node, so they're more connected between themselves and then decreasing the uncle rates again, which seems to have been happening. There's a lot less nodes in the network. Actually, I heard that it was about 3,000, the real number of nodes that's actually running in the network at this point, so very low. We did conclude that some of the protocol changes, the optimizations have definitely helped in terms of the uncle rates. And then we don't have any data on Amazon, so it's really hard to tell. But this is some of the regression analysis that we started running. So this is data from last year and looking at what impacts the most the uncle rate. So definitely the number of transactions, the hash rate, the block size, the number of accounts, but correlation doesn't necessarily mean causation, so it doesn't really matter. And also the rewards and the price of Ether. But if you look at it in the last 6 months, the number of transactions seems completely irrelevant. It doesn't affect the uncle rate anymore. The hash rate is even more highly related. And the block size has also decreased in terms of correlation between that. So we just started doing some regression analysis with all of the variables. This is all the results for all the regression analysis for simple linear regression with all the different variables. And these are the ones that seem to be the most related. So you have hash rate, average block size, difficulty, mining return, uncle mining reward, Ether price, gas limit, and gas usage. So essentially the idea is that with all this data that we've collected, we can actually build a mathematical model and start playing around with the block gas limit and see how it impacts the uncle rates. Because essentially if you have an increasing size of blocks, but the uncle rates are still dropping, then you could potentially increase the size of the blocks to a certain degree. And so this is like building a model, and the idea is that we're going to build a model with this, with multivariate regression, and trying to find what's most impactful. And so from all of these hypotheses, we concluded that maybe the data size has something to do. It's not the number of miners, maybe the nodes as well. Definitely the protocol changes and the GET and parity optimizations have had an impact, as well as some mining strategies that have been employed. There's no selfish mining or no SPV mining as far as we can tell. And there's definitely an increase of miner connectivity, which, yeah, it definitely impacts the uncle rates. But that's it. I don't know if you all have any ideas or anything that comes to mind.
So can we 5x the gas limit or 10x?
We'll see. Depends on what we run with the model and the simulations.
One of the things that I was expecting after this, so you mentioned the gas and parity optimizations. So one of the effects of those optimizations is that it actually breaks the relationship between the block gas limit and the uncle rate. So it actually weakens it. And this is because the block propagation now happens. So the block propagation between the nodes, the speed is basically doesn't depend on the how hard it is to execute the block. It only does the proof of work at the moment. So the only points where the bigger blocks or more complex blocks slow it down is when the miners themselves try to ingest the block. So I would say that it kind of makes sense to me, and also it makes sense to me that it will become harder and harder to use the uncle rate as a criteria for network health. So we need to either, if we still want to monitor network health, we need to find other criteria, which may be stronger correlated to what we want to see. So thank you. That's very interesting analysis. Okay, good. Who did we want to have next? Zach? Yeah, you ready? This and this. So if you want to type and do that stuff, you can just put your laptop here and talk.
Okay, yeah. Hey guys, I want to talk about some testing criteria, right? A lot of this is, some of this is going to be a little redundant, but I just want to make sure that we're all on the same page and we have some clarification as to like what it is we're trying to do here and how we can most efficiently go about achieving these goals that we're setting for ourselves. So I'm a proponent of obviously like doing this in a an accurate and like deterministic manner. So what we need to do is we need to like have a structure to the way that we're testing and validating all of these hypotheses. So obviously first we want to formulate our hypothesis and we want to figure out which problems are valid, like what's worth spending our time on, right? And this isn't about any one particular project or issue that's at hand. It's just in general, obviously time is of the essence for us, and that's the whole point of this. So we need to identify potential solutions and optimizations for these problems after we establish their validity. And the certain optimizations may not be practical. Like we're presenting a lot of stuff, and it's a great idea, but we're kind of trying to come up with short-term solutions. So I think that we should target low-hanging fruit, obviously, like which optimizations are the best and which are the easiest to achieve and implement in a short period of time, and then just repeat this process going down the list, right? So we're going to have these 3 criteria for evaluation essentially, and it's nice to segment these and break them up into groups. So we have environmental factors, and that's going to be more protocol related stuff like the state size and the hashing rate. And another important thing is what can be controlled and what's uncontrollable in relation to these protocol related variables. And then we have computational factors, which are going to account for the resources of a single node, like the I/O, the NIC capabilities, all that stuff, because we can't control the wide area network necessarily, and we can't really control a lot of aspects of the protocol, peering. There's a lot of things that are going to be difficult. And then there are also network factors, which would be like bandwidth and latency and packet loss, the actual conditions that we experience when these nodes are communicating with one another, within the network. So this is kind of like a brain dump, and I'm really just presenting this so we can start initiating some sort of dialogue amongst ourselves, so we can formulate a more structured way of going about testing and validating these things. So, which environmental factors do we consider? How is the nodes available computational or network resources? How do they affect the performance? What's the relationship between pruning threshold and bandwidth? How often does a sync fail with X bandwidth and Y pruning threshold? If we account for state size within the protocol to account for this, and what parameters would result in the most effective optimization, which tweaking and tuning which parameters. And so in regard to cache size, what's the minimum viable cache size? All of these are things that we should go about researching. So we have some assumptions. These are just my basic assumptions I came up with. I wrote this last night just based on some conversations and dialogue from yesterday. So processing the block. I mean, this is redundant because everybody's been talking about it the past 2 days, so I'm not really going to go over that too much. I just want to let you guys know, share with you what I'm thinking. So first, we should establish our testing objectives, identify the assumptions and formulate the hypothesis, what's the bottom line, and which criteria should we absolutely evaluate, and which factors have the most dramatic effects on the outputs. So by identifying those factors, we can understand a few key points, like which optimizations should be prioritized, which are the most practical, which are the most immediately achievable, and I think that's one of the most important. And formulating a test plan, I think that I wrote an example test plan for what we're doing right here. So we can identify the client, we want to test. So I just kind of put this in, and I haven't changed it. Me and Alexi, we had a conversation, and we need to identify what is the criteria for state size. How would you guys define that? Because we can't really do it by actual size that it occupies on a disk, right? Do you have any thoughts on that, Alexi?
Yes, because it is dependent on how the actual clients store it. So I suggested to just number of accounts and a number of storage items and things like this.
Yeah.
Total amount of code.
Okay. So, I mean, this isn't something that we're going to decide right now between the two of us. But before we move on and actually start testing these things, we need to have those variables need to be defined so we know what to look for, right? So within our test cases that we're running, we can write out a test series like this, and we do that on white block, which I will run a demo of. Let me just wrap up though. So using our emulation platform, we can acquire large data sets that are going to be highly accurate or reflective of real world data. And then using those data sets, we can perform additional simulations, kind of similar to what Vanessa was talking about. And the output of one test series can influence our hypothesis and like bring new issues to light. That's just the process. So, but I think we should, it's easier to just be practical, and I think we should just demo Whiteblock right now. So I'm gonna have Daniel come up and help me do it, so I'm not like fumbling around and with keys and talking to everybody. But let's see. Okay. Hello. All right. Yeah, so we log onto the platform. I already have a chain built out, so we should just run the account info. Or let's rebuild it.
While you're working on that, I had a question. Anyway,
Yeah.
so what are your priorities, and where does the state size emulation fit in among those priorities? I think you're going to work with Andre.
Yeah, so we just started talking, initiating that dialogue today. So, I mean, that's something that we'll start working on when we get back to our lab. I have a few ideas, but I think it'd be more relevant to discuss in terms of like after we show what we're doing here. So we're building out this blockchain with using the Ethereum with the Geth client. We're just going to indicate 5 nodes. You can indicate the computational resources that are going to be assigned to each node, and then you can define the parameters of the blockchain, like gas limit or difficulty or whatever you would in a Genesis file, and then it's all dynamically created. And then our platform like provisions all of those nodes, sets them up with the appropriate client, funds the accounts so when we automate transactions and all that, and assigns them each to assigns a VLAN to each one of them, so they all have their own IP. Now we can dynamically configure any of the links between those nodes with packet loss or bandwidth constraints, latency, whatever. We can also add accounts or nodes after it's already been built. So right here you can see like this was the initial balance. There's a transaction count, and all these nodes are up and running. But right now there's, if you run get info, get stats all. Yeah, so it's all 0 right now because there's no blockchain that exists. So when we do miner start, it's going to just start all of the mining process. So if we open a new tab, we can show the process of generating the DAG. So
Joseph, to answer your question, I think maybe Andre can do that. So can you tell us what do you think is going to be the plan?
yeah, so it's actually generating the DAG.
Well, we have to figure out what time it takes to get to a reasonable storage size. And I guess we are interested in testing 2 modes when we have a number of, like a limited number of smart contracts which we inflate. Or the other scenario is that we have actually just a number of dust accounts, but a huge number of them, and then we approach the size of the actual Ethereum blockchain. So depending on how fast we can get to that point and then keep inflating it, we either have to or not have to make a number of modeling assumptions or like simplifications, because on one hand we could use the real Geth and parity client and so on and be as close to the real thing as possible, but of course we'll have to reduce the difficulty, but still if that proves to be computationally prohibitively expensive, then we'll have more and more modeling assumptions, because at the end of the day we are not interested in any security aspect of it, or like even that it's Ethereum or whatnot. We are interested, like given a certain sync protocol, then what is the breaking point of that sync protocol, and then
Yeah, so one of the issues is like, how do we test effectively starting out, because the state needs to be generated and before we start actually testing. So what my idea was is that we create a series of images with the state at size X, and then after those have been pre-generated, we can just import those states into our framework and then start testing with those. So we can automate transactional activity, if you want to show that, and deploying smart contracts as well. So for this, we do, what's that? Do you want to do first? Transactions, yeah. So we'll just show transactions. So we're going to start a stream of transactions between accounts, and you indicate the transactions per second. And it's not like transactions per second that are going to be processed in terms, it's just how many transactions we're going to be sending in total within the network, regardless of how many. That's not the real TPS that everyone thinks it is. But so we're sending 100 transactions per second with a value of 1 ETH. It just started, so we can do get stats past get stats, yeah, past 10. So we can look at the past 10 blocks. It's gonna take a second. So we're watching that, so you can just dynamically observe how this TPS can change, or whatever values or data points you want. One thing to note is we haven't applied any sort of latency or delay or bandwidth constraints or packet loss between those nodes yet. And in order to do that, we also have a tool set for just standard network utilities like ping or iPerf. So we can run like ping between two nodes in the network, like. Yeah, so it's going to ping between node 0 and node 1. So you can see it's 0.05 milliseconds of latency, and now we can apply 100 milliseconds of latency to the links between those nodes, and then we can observe the effects on TPS or whatever. I'm just using TPS as a basic metric that we're all familiar with. So we're applying 100 milliseconds of delay. And then if we run ping again, should be 100 milliseconds of delay between those nodes. We can also apply other network configurations as well. And then if you want to like run iPerf or whatever, we can show you iPerf.
I want to continue back to the question. Yeah,
Sure.
Thanks for the demos.
Okay, do you guys understand the premise? Does it make sense so far?
Yeah,
okay,
it's helpful.
Yeah, so we want to test essentially the syncing as the first thing, and using this framework to test the failure of where does the failure of syncing happens, and kind of get more objective picture about where, what are the criteria, where is the breaking point, and things like that.
Yeah, I'm clear about that. My question is about alignment, because I think I'm pretty clear that Andre and Alexei's priority is getting the data for the state size, increase impacts as it keeps increasing. But I want to get alignment on like where does that fit among your or White Block's priorities. It's like number 1 for them. I think that's pretty clear. But if it's like number 5 on your priority, that's something that we need to align on. So that's what I'm trying to get at.
I think that's like are you asking me what are my personal priorities in research?
I guess whether you or White Block or, again, if it's like if it's number 5 on your interest list and it's number 1 on theirs, then it'll be hard for them to get.
Well, we're going to be working together. So we're going to be collaborating on these initiatives. So in terms of my priorities, that's something that's very interesting to me, but I think my priority is finding out how we can be useful and contributing. So if Alexei sees value in this, then it's my highest priority that we're able to provide value and help solve problems and create solutions. That's my priority, is like So,
Yes.
Yeah, I think we kind of, I think what we're hoping to do is that we are get so basically Zach would provide access to this platform. We have to decide about like the cloud compute bills, like how we're gonna pay these bills and stuff like that. But I think we can figure this out, and you know, essentially to improve the documentation as we go, because there might be some lapses in documentation, and eventually, like the reasons why I want to dedicate Andre for some time for that, so that, you know, I know that Zach also works on other things, but this is why we're bringing Andre in this.
Yes.
So
yeah, so I
Thank you.
created this platform after, because I was working on Ethereum and I didn't have the tools that I needed to do a lot of the low level research that I wanted to do. So this was made primarily for Ethereum, and I've been working and focusing on Ethereum for some time. But I think we should talk about that like offline, because I don't want to like shill everywhere. So.
I wanted to add a comment on testing syncing. So you didn't include this, but something you might want to think about. An important factor in syncing is, at least in Warp Sync, is the snapshot is now so large that just downloading it takes hours.
Right.
And you can't expect a single client to be online for that long. So in the vast majority, like in 60 to 80% of cases, the person you're downloading from will actually disconnect you like halfway through.
Yeah.
And so you need to then go back into pairing and find another like we now have it in place where you can actually restart a snapshot, but then you need to find a snapshot from the same block height. This will be fixed in the next version of Fast Warp, but that's how it works right now. So if you want to test how it works right now, pair disconnecting you is an important part of it.
Yeah, so those are all features and functions that we have implemented.
yeah, I think we're probably gonna start with the geth at the beginning, because it probably and then move on to parity. Maybe by that time you've got already Fast Warp implemented, so we can just do that.
Right. So just some things we need to, I think like the priority is just identifying how we can effectively introduce the state within the environment, so it's not occupying an exorbitant amount of time and generating that state initially from like Genesis. So, but I don't think that's very difficult problem. I think that's probably something we can solve in a couple days of R&D, which we'll get started on immediately. So, but does anybody else have any questions?
I had one, just a quick one. Like, how do you handle different clients, parity versus geth versus others?
Well, we have pre-compiled images that we store, and then we just deploy them based on that client by indicating which client you want to deploy. So what we're showing you here is like just like high level. Like obviously, like when we're testing, we're not using these like build wizards that are prompting and doing all that stuff. We're actually running just scripts that we define based off of like a YAML file or something like that. And then we automate all of the tests. So after you define them in like a test file like I showed, we could just like run all of those tests, and one of them would be like client, we want 100 nodes total. We want 50 of them to have geth and 50 of them to have parity. After you deploy those clients, we have flags like we want to run this many transactions, or we want to do this or do that, and that's what we want to do for this one test case. So we've done a lot of work with ETH research on exploring sharding and libp2p using this framework and using those testing methodologies, and it's been pretty cool experience. So I would encourage you guys to like check out what we've worked on before, because we don't really do any marketing. Like this is like, it's just us like hanging out and talking to people. So but I think that these are valuable tools. They were useful to me, so I think they would be of immense value to you guys as well. And we want to work with you to build these tools and make your lives easier. And I want to open source all of this, and that's a plan. But right now I'm beholden to a board of directors, but I don't want to say anything on the live stream. But we could talk about my personal feelings and plans like afterwards.
Well, you know that this is live stream, right?
Is it live streaming? Okay.
Yeah. Yes.
I love corporations. And I'm very thankful for everything that the board of directors has done for me.
Okay.
I am their humble servant.
Thank you very much, Zach. I think we're really glad to have you on board.
Is there any other
Thank you.
questions? Are we good?
Anyway.
Oh, good. Okay.
Thank you. Then,
I think we have another. Are you guys ready to do one more? Yeah, let's do another EWASM presentation.
You can talk to the podium. I get pretty close. Otherwise, if it's we'll use this one.
Okay. Can we just leave it here?
Yeah, absolutely. Make sure it's on. I can do it. We set it over here.
Testing, hello? Okay. So I was going to talk about metering today, but instead I wanted to show you guys what WebAssembly looks like. And I should zoom in somehow. Yes, yes, metering tomorrow. So that people know that there is some beauty and some sophistication to WebAssembly. It's not just sort of, some bytes of an EVM that hopefully there's no bugs in it. This is some engineering, project, and they have some proofs of some things. Like most languages, they have a syntax. Okay, so this is a paper that they put out when they were first announcing the language. And they have this, I guess, syntax. I'm sure people in this room know about these kinds of things. There's standard ways to define languages. And usually there's a syntax, like we have a syntax in the English language. There are grammar rules. Likewise, they have some sort of grammar rules or syntax to build these programs with. And on top of this definition, so this is a definition of a syntax. I don't know if they have all the rules or if things slightly changed since they published this. On top of this definition, they define, you don't have to know what this is, by the way. Each of these is a rule. And you have to, that if you want to implement the spec, or you have to follow all of these rules. So these rules are for validity. Everything that can be checked statically, they wanted to write down. And hopefully they wrote most of them down. I think there's some more later on for some other things. But anyway, there's some beauty that we're defining something called the grammar. We're defining another thing on top of this grammar. For each of these grammar rules, we're defining these validity rules. And once we define these validity rules, we can prove things like that the absence of undefined behavior. Actually, they have some undefined behavior that they identified, but we know about it. And so the point is we're standing on solid ground. We're not on an EVM. We're on a sort of solid foundation that we can build on. Of course, there are some things like floating point that we have to be careful about, and some things like growing memory that we have to be careful about. And anyway, after they defined these validity rules, and they designed it in a way that you can parse through the I guess, EWASM contract or the WebAssembly module, and in one pass you can parse it based on the grammar rules, then you can check the validity while you're parsing it, and you can also compile it at the same time in one pass, and also you can do it in parallel for each function. So it's an engineered sort of, it's a great engineering project, I think. And they have a compact representation, like 80% of native code size on average. So portable, you can compile it to different architectures. And the ecosystem is growing. There are some growing pains, but it's growing. And there's some beauty in this, these sort of definitions. And there's the execution semantics. These rules, you don't have to know what these are. This is too much, I know. But each one of these is one step in computation. So there are computation steps. It's sort of sophisticated. The computation is actually rewriting rules. So you have some WebAssembly code, and then it goes through these computation steps where you rewrite, where you copy and paste stuff, and eventually you get to your final result. And they have some guarantees that you'll get to this final result.
And I think there's some beauty in sort of defining things and having some sort of foundation and having some sort of solid proofs. You know, these proofs are going to, you know, just like Euclid proved things like 2,500 years ago about geometry, you know, and those proofs are still good today. There's proofs about this stuff, and they're going to be true 2,500 years from now, and, you know, so there's no obsolescence to these proofs. And I guess I just want to, that's all I wanted to say. That's it.
Questions? 1 second. Andrea will give you the microphone.
Yeah, just you know, a layman's question. Basically, I asked briefly Casey and Guillaume that you are using WebAssembly. So WebAssembly gives you some mechanisms and facilities for virtual machines, but also LLVM can give you certain facilities as well. One kind of thing that LLVM doesn't run in browsers directly, but like I guess it can be compiled into WebAssembly that gives you a means to run LLVM stuff in a browser. So like, have you compared using WebAssembly as your primary kind of tool set versus using LLVM as your primary tool set?
Yeah, this was a question. I was not working on EWASM when this question was answered. But yes, there's an effort with Cardano that they want to use LLVM instead of WebAssembly, or they're maybe using both. And yeah, it might be a reasonable alternative. I don't think they design their. Are you talking about the LLVM intermediate representation? Yeah, sure, it's an alternative. I don't know if they have the same properties. I don't know if it's designed to be, you know, for transportation. It might not have the same properties that WebAssembly, but certainly Cardano is justified in exploring it. They change their intermediate representation every version of LLVM. So LLVM 8 or 7, you know, they're starting to work on 8. So their IR is constantly changing, so you have to keep up, or you have to either, you know, move with them, and they might introduce something strange. Yeah, you're right that this is an alternative, and yeah, there are other, you know, the .NET, CLI, there's a few other alternatives that people might suggest. And I think it's an interesting discussion to have, but certainly WebAssembly has some properties that might be hard to beat. So I don't know if I answered your question. I'm just mumbling.
As long as it was considered, I guess I was just curious whether it was seriously considered, and your decision is that the pros of WebAssembly outweigh the pros of LLVM. It's just my personal impression, but again, I'm no expert. It's just LLVM is battle proven, which WebAssembly might be not.
I might be able to. Oh, is this on? Yeah, I might be able to answer part of that as well. And it's not an either/or distinction. You can compile down to LLVM IR and then write a backend for WebAssembly. WebAssembly is the actual virtual machine as opposed to this abstract intermediary, right? So it's actually, I mean, really any modern system is going to go through several of these layers before you get all the way down. So we can absolutely do both. We can also use LLVM IR down to EVM as well. There's nothing stopping us from doing that. And we could actually get, like, you know, obviously WASM was designed from the ground up in a particular way, which is nice, but we could get a lot of these properties moving forward with the EVM prior to EWASM being implemented as well, and plug that then into the LLVM IR as well, write a backend for that. So we could get a lot of these benefits in the meantime, and I agree, I think using LLVM is a good strategy.
So I had a subjective question, a little bit.
Quick announcement. Do you want to do it?
Yeah, sure. They're about to clean up the food and drink. Go get it if you want it.
Last chance for food.
So basically, ignoring sunk cost and all that stuff that you've already invested into, would you choose it again today? And B, do you like it? Do you like WASM? Is it nice?
Yes, guilty on all counts, yes.
I wanted to add more to the decision for using WebAssembly. So LLVM is designed around two assumptions. The first one is that this intermediate representation is ephemeral. It only exists during the duration of compilation. You can throw it away and redo it. The second is that you trust it. WebAssembly is designed on the principles that you don't trust the bytecode that goes in it, and this needs to be standardized. And the reason is that WebAssembly is meant for the web, so you don't trust the code that goes in it. So the whole security design of WebAssembly is way more geared towards adversarial behavior than LLVM is. LLVM will have a number of exploits that aren't discovered because no one is testing it in this field. And I think this is actually the most compelling reason to go for WebAssembly.
Check, check. Last chance for food. Anybody else? And drinks as well. Are we done with programs?